Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Azura binti Abdul Halim. My metric number is DE 2088 and I'm from Group 1, Section 1. I'll be presenting for introduction, technical problem, objectives, single line diagram, and also the environment and sustainable design issue for our industrial power system design. So for introduction, the best distribution system is one that can affordably and securely provide sufficient electric service to both current and potential future loads. The engineer needs knowledge of the loads and the various types of distribution system that can be used in order to build the appropriate distribution system. The fundamental concept the engineer must consider in order to build a power system network based on the provided loads are the structure's existing and future functions, the characteristic of the loads, its utilization and diversity factors, and the needs of the electric utility such as transformer and cable fencing. The fundamental step to design a power system is by developing and documenting it in one-line diagram. One-line diagram requires information such as conductor types and sizes, transformer KVA sizes, ampacity, impedance, and voltages. So for the technical problem of this project the first one is the suitable power system network design to support the given industrial loads. There are three divisions of loads such as synchronous motors, lighting and heating, induction motors, motor control center, and lump loads to build an industrial power network. Each load was given parameters, namely operating voltage in kilovolt, horsepower, efficiency, power factor, and apparent power in kVA for students to calculate the load demand estimation. The second technical problem is the parameter that needed to be considered during planning the power system network. The important components that require consideration are load demand characteristic in order to get the correct transformers VA sizing and cable sizing criteria. These sizing are vital for the power system network and for the construction contractor of the building to provide the correct rating of the transformer, cable, and other protective equipment with exact pricing. Error in providing accurate documentation will lead to the expensive project cost. And the last technical problem is the sustainability of design power system network to serve current load demand and expansion of two division with 60% load increment. The power system network must be able to handle the present and future industrial loads to avoid major replacement and damaged equipment in order for business to operate at optimum level and ensure that the system is capable to carry on without any significant problems. There are three objectives of this project, which are the first one is to develop a single line diagram of industrial power system of the given loads. The second one is to calculate load demand, transformer, and cable sizing of the power system network. And the third one is to analyze the ability of the design system to operate when total load increased by 60% as compared to the existing loadings.
Hello, my name is Novrata Darren and my metric number is DE200047. Now I would like to explain to you about the methodology part of this project. In this slide, it shows the flowchart of this project, which is it shows the step that we take to complete the assignment task. Based on the figure, this project starts with design a single line diagram for industrial power system based on the list of the industrial load given in the assignment task. The single line diagram contains three divisions, which is division 1, division 2, and division 3. Next, the load estimation for each division will be calculated using the utilization factor and diversity factor in Microsoft Excel. Furthermore, the next step of this project is the transformer sizing, which is the proposed size of the transformer will be chosen based on the size of the load. If the size of the transformer did not match the criteria of the transformer, which is the voltage drop at the secondary transformer is more than 10%, or motor full load current is higher than 65% of the transformer full load current, the process of the transformer sizing will be repeated until the suitable transformer size is obtained. Moreover, this project will be continuing with the cable sizing. To choose the suitable cable sizing, three criteria must be met, which are the short circuit current withstand capacity, continuous current capacity, and starting and running voltage drop in the cable. If one of these criteria did not match with the cable sizing, the process of the cable sizing will be repeated until a suitable size cable is obtained. Last but not least, 60% of the load increment will be added to the single line diagram. The operation of the system will be analyzed whether the design of the power network is able to withstand the load increment. The proposed solution will be proposed at the end of this project, and after the solution is proposed, the project will be end. Now let's take a look at the load estimation part, which is we need to do the calculation in the Microsoft Excel. First of all, we need to calculate the maximum load on every division. So we need to create this table, which is contain the value of horsepower, power factor, and the efficiency. With these three values, we can calculate the value of the real power, which is we need to multiply the value of the horsepower with 746. Then we can get the value of the real power. After we get the value of the real power, we can find the value of the apparent power when we divide the value of the real power with the total value of power factor multiplied with the efficiency. Then after we got all the value of the apparent power, we can total up it into each division, which is the first division contains 2,646,000 0.77 kVA, division 2 contains 630 kVA, division 3 contains 2460.44 kVA, and the total load for this SDL is 5737.20 kVA. Now, to calculate the total load demand estimation, we need to do a table like this in Microsoft Excel to calculate the total amount of apparent power. In this table, it contains two levels, which is this is the first level, this is the second level, and this is the third level. In this table, we need to assume the value of the utilization factor and diversity factor. For the utilization factor, we assume 0.75 for the induction motor and synchronous motor because this is an industrial installation. This factor may be estimated on an average at 0.75 for motor. And for the lamp load, heating and lighting, and MCC1, MCC2, we assume the value of the utilization factor as 1. Now, after we calculate all of this apparent power, we need to total up it. Then for the last apparent power, for the total apparent power, we need to sum up of the all of the apparent power, all of the value of apparent power in the level 3, then multiply with the diversity factor, which is 0.9. Then we get the final value is 3660.5 kVA.
As you can see on my screen right now, this is our proposed industrial network design. As you can see from the upper part here is the main incoming distribution transformer T1, where the incoming voltages coming from 33 kilovolt, and then this bus bar here is 11 kilovolt. The transformer 1 stepping down the voltage from 33 to 11 kilovolt, and then this is our first division right here, which contain induction motor. 3 induction motor with 3.3 kilovolt operating voltage, but different in horsepower, which is 400 horsepower, 1000 horsepower, and 1500 horsepower. This division 1 here containing T2 transformer 2, which are stepping down the voltages from 11 kilovolt to 3.3 kilovolt of the operating voltage of the loads. And then for the second division here, we have lamp load and heat and lighting load. But they need 415 volt. So we have a T3 transformer stepping down the voltage from 11 kilovolt here to 415 volt at here. But the load here are different kVA, which is 600 kVA for lamp load and 30 kVA for heating and lighting load. And the third division right here, we have DT4 transformer 4, which is stepping down the voltages from 11 kilovolt to 6.6 kilovolt for our first synchronous motor that need operating voltage 6.6 kilovolt with 100 to 1250 horsepower. And then we have T5 right here, stepping down the voltage from 6.6 kilovolt to 415 kilovolt for the third division load containing MCC1 and MCC2, and also the induction motor that needed 415 volt operating voltage and 250 horsepower.
Hi and very good morning to Dr. Kok. My name is Zoida Habinashri, DE20133. Now I'm going to explain about the transformer sizing for the project outcomes. So for the transformer sizing, we must know the load estimation calculation. So after that, we decided for the transformer arrangement for the T5, T4, T3, T2, and T1, which is the main transformer. So for the next one, which is we must decide the kV rating, which is on the T5 and T2, we have determined on the instruction sheet, which is T2 3.3 kilovolt, T3 415 volt, T4 6.6 kilovolt, and T5 415 volt. So after that, we must to know for the transformer sizing in VA. So for the transformer 5, we divided for the to the 65%. So we get for transformer 5, we get 1.6 MVA. Transformer 4, we get 4 MVA. The transformer 3, we get 1 MVA, and transformer 2, we get 4 MVA. And for the main transformer T1, we get 6.3 MVA for the total connected load. So after that, we decided for the Z%, which is the percentage of impedance in per unit. So for the T5, we use 6%. For T4, we use 6.5%. For T3, we use 6%. T2, we use 6.5%. And the last one, T1, main transformer, we use 6.5% of the impedance. So after we analyze the transformer sizing issues, will be analyzed, which is on the T1 6.3 MVA, the sizing is too big when we match for the 11 kilovolts. The fact is the 33 over 11 kilovolt secondary substation is established where the load requirement is approximately or less than 5 MVA only. So 6.3 MVA is bigger than 5 MVA. So for the improvement, we adding or change the kV rating of the main transformer to the higher level, higher value, which is 22 kilovolts. So for the cable sizing, we used to know the cable position, which is the cable position is after at the secondary side of the transformer. 2, transformer 3, and transformer 4, which is on the every division. So after that, we must to analyze the assumption of the cable condition. We should use the APR type, the 1.5 kilometer distance. We use for the we use to analyze the K1 until K4, and also we assume the short circuit capacity is 200 times the rated current. And after that, we go for the cable sizing. So for the sizing, we must to analyze the load connected current. After that, we must analyze the short circuit capacity criteria, and after that we must to know the ICCC, which is the continuous current capacity result. So after we analyze on the ICCC that we get for the division 1 is the infinity, division 2 we get the infinity, and division 3 we use the standard cable size, which is 300 mm square with ampacity 286 ampere, and we get ICCC to 3.49. So for the discussion that division 3 with cable 3 is safe because the I3 is over than I1, which is the load current. So for the transformer 2 and cable 1 and cable 2, we must to do some improvement, which is maybe we need to increase the supply voltage, or because of the overload supply overload load, so we must to use every motor that there must have an individual sizing transformer. So this is the design after we do improvement, the change of the main transformer, which is the voltage supply is 22 kilovolt, and DT2, which is we use the individual setting transformer on the load. Also same for the division 2, but we change for the siding transformer on DT3 because the supply voltage is 6.6 kilovolt, so the minimum siding transformer is 4 MVA. So for division 3, they have no changing. So we go for the transformer sizing, new transformer sizing. We must to analyze the supply voltage and also the adding transformer, the siding transformer, and we calculate lah. So after that, we go for the cable sizing. So for the cable sizing, we must analyze the load current connected current I1 new. So which is analyzed that for cable 1, 138.92 ampere, cable 2, 110.22 ampere, and cable 3, 215.23 ampere. So we do for the short circuit capacity criteria and the continuous current capacity results. So after that, we get the I3, refer to standard cable size. So we discussed that every cable in every division is safe to use because their I3 ICCT is bigger than I1, which is the load connected current. So on the cable 1, we use the 3-core aluminum APR type 185 mm squared. Cable 2, we use 3-core aluminum APR type 300 mm squared, and cable 3, we use 3-core aluminum APR type 300 mm squared. So that's all from me.
Environment and sustainability design issue, we found out that the design issue that have been faced during the completion of this project are the energy efficiency of the motor, appliances such as motor control center, lighting and heating, and also lump loads. The impact of energy efficiency on industrial power system network are a waste of electrical energy and increasing power factor, which can lead to high tariff charges. Besides that, we also found out an issues of our design that the original design structure are not recommended for future business expansion based on our feasibility study that have been made by all of the group members. Therefore, the design has a weaknesses where the industrial network like transformer and cable sizes are unable to support 60% of load increment and another 2 division expansion. Therefore, in order to solve the design issue, as I stated before, the proposed solution for lighting loads are by replacing the fluorescent with LED bulbs. Besides, using a timer or a photocell system assists in automatically turning off the lights during the morning for outdoor lights. Furthermore, during daylight hour, an industry system is able to use the advantage of natural light by placing work areas near windows. For indoor lights, the solution can be made by adjusting light level or installing motion sensors so the light will go off automatically in a room with no worker. On top of that, the proposed solution for motor efficiency are select the lower power motor but it can operate with a higher load factor near optimal efficiency to assist justify the motor replacement. Other than that, industrial companies can also increase motor efficiency by using variable speed drive motor system instead of traditional motor when loads vary significantly over the course of daily use. Moreover, heating load efficiency can be improved by regularly doing the maintenance of the machines, and the temperature setting of the machine must be inspected constantly to ensure they are not higher than necessary. Last but not least, for the standard network structure, the most recommended for a very widespread network with the major future expansion is the open or closed loop, also called as a primary loop system. So this is our primary system network design after 60% of the load increment.
Okay, we go for the conclusion. So the goal of this project is to build a method for distributing power in the industry, which is we build a method, we design the system. So the design equation we develop and create using Microsoft as a spreadsheet. And the design of the industrial network, so which is the single line diagram, also has been designed in that software. So the Excel-based calculation method that was designed to examine whether the calculation processes match the requirements as the employed in the actual operation electrical power distribution network is also used in the comparison research. So the final proposed network design has the ability to support the additional 2 division with an increment of 16% of the existing load. So this paper also recommends several types of load that can use for the additional division suitable to enhance the environmental and sustainability issues. Thank you, that's all.